everybody, this is an introduction to the specific heat lab. So once you log into Pivot, this one is going to be called Using Specific Heat to Identify an Unknown Solution, PNW. So I'll select this one, and the lab is here. Measure the specific heat of a solution. So we're going to have 6 different solutions. We don't know what the specific heat is. The goal is to take some measurements, calculate the specific heat from our measurements for the 6 trials, and then we can compare that to a list of known unknowns here and figure out which unknown liquid is A. So six different trials. They're in random order, the 6 trials. So we'll calculate the specific heat for all 6, and then we'll compare that to this table and figure out which one is liquid A. Was it trial 1, 2, 3, 4, 5, 6, that sort of thing. Okay, more about that in just a minute. So let's take a look at this actually. What do we have here? Here's a scale. We can get the mass of our sample here. The lava lamp is just for your viewing pleasure. It's not actually used in the lab. Here the temperature is displayed in degrees Celsius. And this sample here is in a styrofoam insulated cup. And you'll see in a minute, this is on a heating plate. There's another heating element that goes in the top. So we'll be able to measure the mass of the sample. We'll know what the initial temperature is. We'll start heating it up. We can see how long it takes to reach another temperature. And we know the rate that this is being heated up from the information up here. The heating coil adds energy to the liquid at a rate of 21.1 watts. So watts, remember, that's joules per second. So if you measure the amount of time, and you can do that because you have a stopwatch over here, you measure the amount of time, and you know the rate that energy is being added, you can figure out the total energy that's added. Okay? Note that this is measured in minutes. So later on you'll have to convert that to seconds. Let's just run through it one time and you can see. So this is in, let me just play it. So there's the sample. Oh, so that's the mass of just the container, and it's measured in grams here. Okay. The liquid's being added. Okay, so now you know the mass of the container and the liquid. Really, you're going to need to know the mass of just the liquid eventually, so you'll have to subtract those. Okay. So we're starting to heat it up a little bit. Okay, so now you notice the lid is being put on. This is our thermometer here. In a minute, in a second actually, there's going to be another heating element put in here. So let me play it forward a little bit. You can see the temperature is going up because the liquid wasn't at room temperature to begin with. Pretty close, but not exactly. Okay, play it a little bit forward again. Sort of, the temperature started to stabilize a little bit. Let me slowly back it up. I want to get to the point where the heating element's not in anymore. Okay, so it looks like it's out. Oh, there, almost in. Okay, so we're starting around 21.64 degrees. I can back this up slowly. Okay, 21.64. Okay, so I'm going to take that as the starting temperature. I can even advance it one more to make sure. Okay, 21.64. That's where I'm going to start taking my time measurements. So this liquid, and again, you know the mass of it, is starting out at 21.64 degrees. I'm going to reset the stopwatch to 0. Remember, just click here to set it to 0. And then I'm going to let this run. So we're starting at 21.64. You would have known the mass. I'm going to play this, and you can see it quickly starts heating up. So depending on the specific heat, certain specific heat will heat up quicker. Other specific heats will heat up less quick. The time is still running here. And I'll go close to the end here. It's still heating up. I'll stop somewhere there. Okay, So 15.18 minutes, you're going to want to convert that to seconds. I'll leave that up to you, 60 seconds in a minute. So we've gone from the starting temperature, so the initial temperature, up to this temperature in a time of 15.18 minutes. Again, convert that to seconds. So knowing that amount of time and the fact that we're putting in 21.1 joules every second, you can figure out how much heat was added. And from that, you can calculate the specific heat. Okay, and there's 6 different trials here. So you'll have to do all 6 of them. So each of these different samples has a different specific heat. Now we're assuming a few things here. We're assuming that all of that heat from the device here is just going into the liquid. That may or may not be a great assumption. It's probably pretty good. Some of it probably is escaping. Some of it's probably heating up the insulating material. And again, not a complete perfect system here. All the energy is not just going into the liquid, but probably pretty close. Okay. Another way of thinking about it is if all of the energy was going into the liquid, it would heat up quicker than this. So keep that in mind when you actually calculate the specific heat. Okay, let's look at the theory behind this. So here you see the formula from class. Q, that's the amount of heat that's going to be added. And this is measured in joules, and you'll have to calculate that from knowing the power of the device and how long it takes to heat it up. You'll be able to get that measured in joules. M is the mass of the sample. So usually we use kilograms in this class, but it's more appropriate in this lab to actually use grams. So this is in grams. C is the specific heat. So that'll be joules per gram degrees Celsius in this lab. And then the delta T is the change in temperature, and this is going to be measured in degrees Celsius. Okay, so let me just do one more step of algebra here. Let me solve for the specific heat. That's what we're trying to find in this lab. Specific heat is Q divided by M times delta T. So for each different trial, and again there's 6 of them, you'll be able to initially measure the mass, the scale is given, the change in temperature you'll know, and the amount of heat you'll have to calculate from the power, times the amount of time that you have. So then you can calculate the specific heat this way. So different liquids have different specific heats, and in some cases you could actually determine what the liquid is just based on the specific heat. Okay, so let's go back to the lab. Okay, so you saw how I got the mass, and then once the actual top heater part goes in, you can start the clock from that point and figure out how long it takes to reach your final temperature. Okay, you'll have to go through that for all 6. So, answer these questions. What quantities, including units, so make sure you include the units you're going to use, will you need to measure to determine the specific heat? And then describe how you use these quantities to find the specific heat. And really the theory part, I gave you pretty much the answers there, right? So make sure that you look back at that if you forgot already. Outline the experimental steps you'll use to measure the quantities. So this is kind of like the procedure. 1, say whatever you're going to do in step 1. Maybe that's measure the mass of the container. Step 2, measure the mass of the sample plus the container, that sort of thing. So go through there and detail it. Maybe if you were going to give this lab to somebody to do, how would they perform the experiment? So, include enough steps here that somebody could follow what you've done. You could either type it out here or, do your work on a piece of paper, take a picture of it, upload it. Whatever you want to do, that's completely up to you. Number 3 here is describe how you determine the amount of energy added. Okay, well, again, the power, the 21.1 joules per second. If you know the amount of time, you could figure out how much heat was added. That's what Q is in that formula. Okay, now the data table, it's up to you to complete this data table. So you'll have to add different columns for these different trials. I just have a kind of a skeleton here. So I know I'm going to have to measure the mass of the liquid. So, probably you'll have to have some kind of column with mass. I mean, you might even have a column for mass of container, mass of container plus liquid, mass of liquid, however you want to do it. So that's just a clue. You'll have to have something with mass, right, and some other ones, some other quantities that you're going to be measuring. Make sure, though, that you have a column somewhere here that is the calculated specific heat for each unknown. That's what we'll be looking at. Okay, so make a nice data table. Make sure you put the units and things like that in. Now, you have some experience with these tables. You could actually use the table to do your calculations if you remember that from previous experiments. Okay, hint, Q is equal to MC delta T, and what you're trying to find is the C part. Okay, so make sure you'd go through, make a nice data table, and then once you get the specific heats, you want to figure out which one of these is unknown A. So unknown A has a specific heat of 4.184. So you calculated specific heats for 6 trials. Which one of your 6 do you think is 4.184? And remember, you're assuming that all the heat is going into the liquid, and it's not. So will the specific heat that you calculate be more or less than you think it will be? You'll have to think about that. Think about the actual equation that you have. Okay, once you get your number, and then this part is figure out the percent difference between unknown A and what you think is unknown A. Okay, part 2 is analyze the differences between experimental and published values. You have access to the whole lab. You could actually read this part first to give yourself some insight into what experimental uncertainties you might have. Okay, so the first one, Rosa suggests a source of error. Some of the energy from the heating coil is lost between the insulation of the container and is not perfect. So what type of error will this cause? In other words, will the experimental value for the specific heat be higher or lower than this? And then explain your reasoning. So make sure you use complete sentences there. Don't try to be really frugal here. I mean, take some time. This is 10% of the overall lab, right? 4 out of 40 points. So spend some time answering that one. It doesn't have to be pages and pages, but make sure you address this whole concept and explain why you think that. Number 2, Max forgot to subtract the mass of the container when he measured the mass of the liquid. How will this affect his results? And don't just guess. You have the formula for specific heat. What if the mass is more than you thought it was? How would that actually affect the specific heat that you calculate? Okay, and then suggest one possible source of error that would cause the experimental value for a specific heat to be less than the actual value. Okay, so what assumptions did you make? I mean, think about the heating device. It's rated at a certain value. Is it really that value? What would happen if it was more than the value or less than the value? That sort of thing. Okay, good. So I think you'll have some fun with this one. It's kind of an investigation of specific heat and trying to figure out which one of your 6 is actually closest to 4.184 joules per gram degree Celsius. Okay, if you have any questions, email your lab instructor. Bye-bye.